and these were the values. Actually, maybe Israel can remind me of the value. This was
I think it was
5K.
Yeah, I thought it was 4 and 3, right? For a total of 7.
Oh, was it 4K? I'm sorry, yeah. 4K and 3K. How much was these? They are 2.
Yeah, that I'm trying to get right now. If
Right.
nobody, because
Okay.
loading up Wolfram. 201 and 86K.
I'm sorry, say that again. What was R2?
200K and then the others 86K.
220K
No, just 200K.
or 200K?
Yeah.
200K and
86K.
86K. Very good. Thank you very much. Okay. So this is CE. That is CO. And that is C in. So that is the circuit. Okay. I was IC or IE was 1 milliamp. Beta was 199. Sorry. Let me just put it to silence. And what else? That was all. Well, alpha would be 0.995. If beta is 199, then alpha is this much. That you can calculate yourself. Okay. So again, this is how we arrived at these values. That the 4K was given. Obviously, 4K was the load. We were given that load, and the 12 volt we were also given. And then we said if VCC is 12 volt, let's assume that across the transistor there is about 6 volt drop. That is midway VCE. This is of course VCE, as you can see. So VCE was we can assume to be about 6 volt. So we take 6 volt from the 12 volt. The remaining should be across this resistor and that resistor. Is that the path we took, Israel? Is that what we did yesterday?
Yeah, pretty
Okay.
much.
Yeah.
Dr. Kasai,
Yeah.
didn't you say that the halfway voltage was 5 volts,
Oh,
not
okay.
6?
I'm very glad. Yeah.
I think that was 7 volts, and that the 3K had 5 volts.
No, I think Jillian is right. We said 5 volt here. The remaining was 7 volt. Am I right? Actually, we may still have it.
Remaining should have been 3, and then the VB would have been 3.6 because you said that, or we agreed that we'd have the drop across it be 0.6.
Yes, we did say that this is 3 volt. Yes, I did remember that. And then this would be 3.6. So did we assume that the VCE is 5 volt or not?
Yes.
Yeah.
Okay. Okay. So we went exactly what we did yesterday, and we said this, the point at this point was about 3 volt. And if emitter is at 3 volt with 1 milliamp, that is obviously 3K, and therefore this voltage would be around 3.6 volt. That's good. And then based on that, then we said, okay, this voltage 3.6 volt, that voltage 12 volt, and then we can say that 3.6 equal 12 times R1 divided by R1 plus R2. From here, we determine what R1 over R1 plus R2 was going to be, whatever number, just 3.6 divided by 12. And then we said there is yet another relationship. This is relationship 1, another relationship 2, which is R1, R2 divided by R1 plus R2 must be much smaller than 1 plus beta times 3K times RE, and that is 200 times 3, that's 600K, and that suggests that R1, R2 divided by R1 plus R2 is around 60K. Because it's much smaller than 600K, we would take that as 60K. And this is what we did yesterday. Now, today, we want to decide on the value of CE, the value of CN, and the value of CO. Any questions so far? Okay, very, very good. Very good. Now, so let's now talk about CE. We do remember that we said we have to have this this resistor 3K. We have to have it to save our transistor from burning. Really, it has no other benefit. It just does not help at all, apart from saving this transistor from burning out, from drawing too much current. Because what we mean by drawing too much current between base and emitter. See, for whatever reason, that when the voltage at the base goes up, goes high, obviously this base emitter diode, this diode, will more current will be flown through this junction. When the base voltage goes high, this diode will have higher current. The base emitter diode will have more current. And when there are more current through this junction, there's obviously the junction gets hot. And when junction gets hot, there will be more current flown through that junction because more carriers will be released. So then more current will make the junction even hotter. When it goes even hotter, then there is more current flow, and so on and so forth. It will just keep on accumulating until it would burn out this transistor in very short period. So how do we solve that? We just put a resistor here, a resistor at the emitter. So when the voltage goes high and there is more current flown here, then more current through this 3K will develop more voltage across this 3K. That means this voltage will go high, will go up. Whatever it was, it will now go up a bit. And when this goes up, then this base emitter diode will be less turned on, will be less forward biased. Therefore, the current will fall. Does everybody understand that? Anybody have any question at all? No? Okay. So that is why we put a resistor here. just to save this transistor from burning out. Now, but is this a good thing? I mean, is it really helping anybody? Not really, because now that, okay, say we biased it somehow. We biased the transistor as you've seen. This bias, DC bias is good. Now we're applying AC. When we apply AC, that voltage, that base will go up, of course, because of this signal that is applied. So this will go up. Now, when it goes up, obviously there's more higher current due to AC, not DC anymore. So this extra current is simply due to the signal, due to AC signal that we have applied. So more heat will be dissipated in this simply due to our signal. And that is a bad thing. We don't mind the heat dissipation from our battery, but we don't want any of our signal to be wasted in the form of heat, because more current here, there will be less left for the load. I mean, however much heat is drawn from here is of the energy that we are supplying. Our signal is too precious. We don't want our signal to be wasted. Does everybody follow that too? What I am saying? I am saying that when this voltage goes up because of the applied signal, that will obviously increase the current, and that current is simply due to the AC signal, and we want to prevent that. We don't want that heat dissipation because of AC. Tell me if you have any difficulty understanding that. Great. So that is why we put this capacitor here. This capacitor only helps so that when for DC purpose that we needed this resistor here, we needed everything for everything. When we put a capacitor for DC purpose, this does not exist, as if it's not there. It's not helping anybody, it's not harming anybody, because it's an open circuit for DC. But then we have to make sure for AC, this is shorted to ground. For AC, this resistor is not there. This resistor is bypassed. When it's shorted to ground for AC, that is not there anymore. For AC only. So that is the purpose of putting CE there. So let me face you to ask if everybody follows the purpose of that capacitor. Good.
Yep.
Very good. So so we really want to do something that for AC, that capacitor is not there. For DC, it is there. Great. Thank you. Right. So how do we make sure that for AC is not there? Okay, now that is the beginning of our discussion today. So we want to make sure that this capacitor is really short circuit. This capacitor is short circuit for AC. How do we do this? That means this capacitor's impedance is very, very low. That is how we're going to tackle this issue. We're saying that we choose the value of this so that its impedance is very low for AC. What is the impedance of CE? The impedance of X of CE is equal 1 over 2 pi FCE. Correct. Now, this impedance must be very, very low for the frequency of the signal. Right. Now we're coming to a more important something else now. Firstly, when we say XC must be very, very low, how low do we mean? We mean XCE. Okay, sorry. We mean XCE must be much smaller than the resistance across it. Across it. What do I mean by that? If I have a resistor there, and then I put a capacitor there, say this is ground. If I want this impedance, if I want the impedance of this capacitor to be very low, to be shorted to ground, obviously I mean with respect to this. For example, if this is a mega ohm, then kilo ohm is short, basically. But if it's only 100 ohm, then I would expect this to be 1 ohm. Can you see what I'm saying? So it's a relative thing. So the impedance of this capacitor is only in relation to how much this resistor is. So really, I want X of CE to be much less than the resistance across it. You all follow? Now, let me draw the this is RE. Here, I have RB. Can you see this? When I want this, the impedance to be very small, I mean much smaller than the resistance across it. Now this resistance is also, so this resistance is one resistor from here to ground. The other resistor is that to ground. So really, I have two resistors in parallel. So in fact, I'm having RE in these two resistors. This little one is tiny RE, little RE, and this is RB, and this is RE. Can everybody see this? But then this RB is not really the same RB as we must. This RB will not be that value that we should be bringing in series or in parallel with this RE, because that would not be fair. What do I mean by that? I mean, the current that flows through here is not the same current that flows through there. Usually when we have resistors that we compare together, it's for the current that flows through them are all equal. But here, the current through this RB is 1 plus beta smaller. So this RB must be divided by 1 plus beta. That is the resistor value that we should be considering. So basically, I want XCE to be much smaller than RE parallel RE plus RB beta plus 1. I have to pause, and I'm sure I must have confused some of you, and therefore, let's have a fight. So let me face you.
So I assume that RB is our equivalent for R1 and R2? Like,
Yes, RB
okay.
is R1, R2
R7?
parallel.
Okay. All right.
RB is R1, R2 parallel, which is 60K, yes. Seriously, is everybody happy with that?
Let's go over what little RE is again.
Okay, we go through little
Yeah.
RE. Yeah, let's just get the most difficult part. Did you honestly understood and followed? You see, when we say this resistor, this must be in parallel, because from here to ground, and then from here to ground. Now, from here, what we see, what impedance do we see? We see little RE and then RB. Okay, when we say RB, obviously we must be fair. This RB value does not tolerate the same current as this RE. The current through this is 1 plus beta smaller than this. So we must really take this RB a comparable value. And that means RB must be divided by 1 plus beta. Now, as Israel just asked, what is little RE? This little RE is nothing but RE is delta. Okay, why delta? Just VBE over IE, which is 26 millivolt divided by 1 milliamp, which is 26 ohm. When I say VBE, I mean V gamma, or remember okay, that was, call it V gamma. That was, how do you say, Q over KT, which is 26 millivolt. That is what we put here. So RE is gamma over IE, which is 26 millivolt over 1 milliamp. Little RE is just 26 ohm. That is always the case. So if everybody is happy, and if everybody is following, and if you have no questions, we can now continue.
How did you get 26 millivolts for V gamma?
Sure, that's exactly Q. This Q, I wrote here, Q divided by KT. Because remember, the current through base emitter, I is equal I0 E to the power Q V KT minus 1. And therefore, this Q over KT times the voltage divide this is 26 millivolt if you substitute values for the room temperature. You follow?
Yes.
Good. So let me just rewrite here. Okay. $26.03 3K $60K divide by 200, and this is the capacitor CE. Now we say XCE must be much smaller than 3K parallel 26 plus 60K divided by 200, that is 60,000 divided by 200. So 2 zeros, 600 divided by 2, 300 plus 300. Right. Now, when we say this, okay, 3K parallel to 326 ohm. These two resistors, when they are in parallel, the result should be around 326 ohm. So we must say XCE must be a lot less than 326 ohm. The impedance, that is to say, we must choose a capacitor value that when we put that capacitor there, its impedance is a lot less than 326 ohm. That is what we're saying. That we are saying 1 over 2 pi FC must be less than, a lot less than 326 ohm. Okay, therefore we can say from here, we can say C must be a lot less than 1 over 2 pi F 326. Now the question is, what is the value of F? What value do we select for F? Is everybody good so far?
Yes.
Great,
Yes.
great. So now the frequency of, for example, for audio is anything between 20 hertz all the way to 20 kilohertz. I'm just round the figure. Now, we want this C to be even, to exhibit low impedance even for low frequencies. Seriously, because it will obviously, any capacitor, even small capacitor, will show low impedance through high frequencies, of course, because as the because don't forget, Xc is 1 over 2 pi Fc. As the frequency goes up, the Xc falls. So at high frequency, that impedance is low anyway. So we shouldn't really be considering F maximum here. When we say F here, we must really consider that minimum F, not maximum F, because for maximum F, impedance is low anyway. So if we make sure that the impedance is low even for F minimum, then we are secure. We are good. We must not consider maximum F, we must consider minimum F. But for obviously, no audio signal goes as low as 200 Hertz. It is always good to consider F min as 100 Hertz. That is pretty much safe. So let's just substitute. C to be much smaller. I'm sorry, not much smaller, much bigger. You see, when we said 1 over 2 pi Fc and all that, we should say C must be much bigger. C much bigger than 1 over 2 pi F minimum times 326 ohm. So C a lot bigger than 1 over 2 pi times 100 times 326. Who wants to calculate that? I would say
4.8
4
micro.
Thank you. So C is 4. Okay, this not C. This is 4.8 microfarad.
Yes.
Therefore, C, a 40 microfarad is what we should choose. That would be the resistor we choose. The capacitor, sorry. That would be the value of the capacitor that we need to choose, or even bigger. Well, at least 40 microfarad. Okay, so I need to pause here and tell you something. So let me just face you. If you followed what I said, now, because you may say, well, what am I supposed to do in the exam then? I mean, if that was the question, which resistor value do I go by? I mean, because you can tell me that you keep on sort of approximating everything. You're not giving me any solid ground. You're making F minimum as 100 Hertz. You're making the resistor values of this much. So give me a better answer. Did you notice that even with those conservative values, I arrived at a capacitor about 40 microfarad. So if you only said, if honestly this is a fact, if you said to me that, let me just RE, RB, CE. If you said that the value of this capacity, this CE capacity, that XCE must be much smaller than the impedance that it actually sees, that the impedance is this resistor to ground plus or in parallel with 26 ohm to ground. So if you told me that XC is RE parallel RE, and if you did this CE, you would calculate to be around 100 microfarad. Instead of going through all these RB divided by 1 plus beta and all that I did, I gave you a very accurate figure. But if you just went and said XCE must be less than RE parallel small re, in which case the capacitance that you would decide you would get the value would be about 100 microfarad. Who is to say you're wrong? Who is to say you're wrong? That was the point I wanted to bring to your attention. Because as long as you have a bigger capacitor that meets that requirement, your circuit would work just as good as the circuit I designed. Kenneth, are you happy with that?
Yeah, I think so, yeah.
Thank you. Whenever I'm in trouble, I ask you for help.
Well, I did have a question, but by the time I got back, my computer blue screen, so when I got back, the answer was, my question was already answered. But I was trying to figure out what the small RE was, but that's the resistance across the transistor.
That's correct. Across the base emitter.
Yep.
Yes, you're right. Okay, Stefan, Christopher, Isaac, Andrew, Joe, Mario, and I mean, are we all good?
Yeah.
Great, super.
I understand this pretty thoroughly now. So yeah.
Thank you very much. Very good. So we've tackled CE, which is the most difficult of all. So really, I mean, Israel, you're looking as you're not very happy.
Oh, me? No, I'm plenty happy. I'm just I'm working on this also on Wolfram in the back too. So I might look like I'm zoning out a tad bit. Yeah,
that's fine. No, you're testing to see whether you get the 100 microfarad that I mentioned. You're testing that.
I'm testing to see why Wolfram's not simplifying the way I think it should. Because like I remember when we were doing this on the homework, I was able to do it, just on paper and with the calculator, but then trying to do it in Wolfram, it didn't give me the same values. So I just thought that was weird.
Okay. Right. Incidentally, you are really not allowed to work with Wolfram in the exam.
Oh, that makes sense. We shouldn't need to. So
yeah, of course, yeah. Anyway, so let's now go. I mean, if everybody is happy, which I'm glad you are, let's go and try C in and C out. Well, fortunately for C in is much simpler, and C out is exactly equal. Simple as that. So C in. Okay, C in. Where are you, C in? Okay, this C in, the impedance of this capacitor must be smaller than the input impedance of this whole circuit. You see? Because this signal, okay, what is C in for initially? Let's see, what are we putting C in for here? We are putting C in because whatever DC that may be superimposed with the signal. See, that's all we are worried about. We are worried that the signal that we are going to apply to this circuit, the signal that we are going to apply to this circuit will have some DC value with it, which always does. We don't want that DC to ruin our DC, because this was meticulously decided on. This was so precisely calculated. We don't want this to be varied. We don't want this DC value to vary, because that would be our quiescent point varied. We don't want that. We want this to remain intact, only the AC signal to take it up and down. That's all we want to do. So any DC value from this source must be blocked. Now, do you see that when I say DC to be blocked, but then AC needs to get passed, correct? So the frequency of that, we can still take that frequency as 100 Hertz. That we understand. But was it Christopher? I can't remember who was it, Philippe, who said, why are we taking this 300 ohms? You all, let me actually do this. You all calculated the impedance Z in the lab. Actually, you actually not only calculated, you measured this Z in, that it's seen by this whole amplifier, by this amplifier, to be around Z in was 8 or close to 8K. You all remember that. Some calculated to be 8 point something, some 7 point something, around 8K. Now, so if I was to draw the amplifier, I can say that really that is the impedance. Okay, let me draw it bigger. An amplifier can be shown as the 2-terminal in, 2-terminal out. Okay, that is really Z. Now here, our signal is applied. There. This is V in. This is RS, the series resistance with the signal. So when we say that the capacitor which was put there, that capacitor, which is actually, capacitor is put here. That is C, must block any DC from here with the minimum frequency, and this must block DC but must also allow AC. Right. If the now in actual fact, when I calculate the impedance of this capacitor, so I'm going to redraw this is RS, this is XC, of course, it's in the form of, and this is Zn. That is really what we should be looking at. And that's why I said now, taking these into account, which is honestly far more involved than you can imagine, which I am really not going at this stage confuse you by going into this. I'm just asking the impedance that you must be considering, Zn, that you must always bear in mind, just take it as 300 ohm. That's all. And you'll be safe. You'll be good. You don't have to ever know why. If any of you ever want to know why, I can sit with you and show you that is the case. But it's just fantastic, just fine, just good enough for you to say that the impedance of that capacitor should be less than 300 ohm. That's all. Are we good? So XC must be a lot less than 300 ohm. 1/2 pi F min Cn must be much smaller than 300, or Cn much bigger than 1/2 pi F min times 300. Now, if somebody tells me what the value of that is, please. Actually, I can do it here.
I was gonna say 5.3 micro.
All right, thank you. 5. So this is 5.
53, yeah.
Yeah, 5.3 microfarad, and I would take 50 microfarad here. For both C in and C out, I can take 50 microfarad. Now we'll be good. All right, that is absolutely fantastic.
How come for the capacitors, when we say that it's much, much greater or much, much less, we're only doing 10 times versus with resistors, we do 100 times?
We don't. With resistor, we also do 10 times.
Or maybe I'm just looking at it wrong then.
No, with resistor, we said 600K, and then we went down to 60K.
Oh yeah, never mind. Okay.
Well, you would be right if that was the case. We shouldn't discriminate. When we say much bigger, we have to have, I mean, when we say much bigger, I mean 20 times, 10 times, something like this. But as you guessed, with bipolar transistor, it's just we can't be that precise, that accurate, that certain. Things are not that certain. But fortunately, we have yet another device that we don't have to have any worries, any problem with that. And that now leads us to our next device, which is op amp. So before we do, are there any question regarding what we did yesterday and today before I go to op amp. Oh, I forgot. I should have looked that mobility thing up for you, which is, I will. I promise you tomorrow when we meet again, I will have that graph for you. And I will also, I'm hoping that, I mean, definitely we won't finish op amp today, so we will have another session tomorrow afternoon.
You know, come to think about it, I do got one question kind of. I know we're working with BJTs right now, but does this work kind of the same way with like the field effect transistors?
Oh, no,
No?
no, actually, no. The field effect transistors have their own, well,
Sort of
very,
amplifier?
well, they have their own issues. But you're right. I mean, biasing bipolar junction transistor is far more vulnerable, if you like the term. I don't know if that is the right term, but we have to be very, very precise with how we bias it. No, in fact, with the field effect transistors, it's not that bad, actually. It's not that bad. But again, see, because we are using bipolar junction transistors as an amplifier with all FET devices, we don't use them as amplifiers. We use them as switches and so on. So it's more of drastic switching on. With the switch, we want on or off. We have no issues in between. With amplifier, we have to make sure that each bit of a signal is religiously, responsibly amplified.
Okay.
Yeah. All right. So let's now. Are we good to start with op amp then? There's no question. Great. Right. So we can put all this behind, and we can say op amp is a device that has two inputs. The two input means the inverting terminal and the non-inverting terminal, and just an output. So V in 1, V in 2. So we have to supply this VCC plus and VCC minus. For example, if I connect this to plus 15 volt, I must connect this to minus 15 volt, both with respect to ground. So, for example, minus 15, plus 15, that kind of thing. All right. This device has many characteristics, but the most important characteristic is very high gain, and two, very high input impedance. Now, that's the fact that we say very high input impedance, that means current through the device I is always equal 0. Simple. Of course, the third characteristic is very low output impedance, but these two are really, really helping a lot. And since the gain is so much, the gain is so huge, that if we applied 10 microvolt here, there, we will get 1 or 10 volts out. Imagine, honestly, just consider that for a moment. 10 microvolt is such minute, small amount of voltage, immeasurable sometimes. And yet, let me actually see who's, I want to go and mute who is 10 on. Okay, mute this guy. Arthur, I just muted you. Sorry about that. So, so if I just apply 10 microvolt there, or 10 microvolt there. See, the reason I'm saying this, because we proved it to you that it doesn't matter, it does not matter at all, whether I apply the voltage there or apply the voltage there, because this device always receives whatever I apply as the difference between the two. For example, let me just kind of quantify this. If I apply 10 microvolt there and put this to ground, and then I put 10 microvolt there and put this to ground, what is going to be seen by this device is 10 microvolt minus 0. Here would be 10 microvolt minus 0, which is plus 0. Aren't these two the same? So the applying signal to any of the terminals really don't have that much difference. So the point I'm trying to say, when I apply at this second, when I have this op amp in its raw form, which is called open loop, when I use it in open loop form and I apply a very, very small amount of voltage here, 10 microvolt, it will give me 10 volt out. Well, that's huge. That's really, really magnificent. That's far more gain that I can possibly tolerate. And not only that, this is something we never said it before. In fact, I purposely, I most certainly, I don't need such big gain. I don't want that amount of high 1 million times gain. You know, because this is not controllable for me. I won't want to apply microvolt here and then receive 10 volt. Because when I apply 10 microvolt, what if it goes up to 15 microvolt? See that this point I'm bringing to your attention is for the first time. I haven't said it before. I really want you to pay attention. If the 10 microvolt goes up to 15 microvolt, is that really a sin? Is it a crime? Can you tell me that it won't ever happen? 10 microvolt can easily go to 30 microvolt without anybody even noticing, because the difference is still very, very small. So if the 10 microvolt that I want to amplify goes up to 15 or say 18 microvolt, which is not so unusual. Will I get 18 volt here? If the 10 microvolt goes up to 18 microvolt, which is very, very probable, will the output go from 10 volt to 18 volt? The answer is, oh no, it cannot. How can it go if the maximum voltage I'm applying here is 15 volt? That is why I don't want such a big gain. In fact, it's not beneficial. In fact, I shouldn't be using this device with such massive gain. I don't think it's at all worth having that. That is a very, very important point about op-amp. Although it has a fantastically large gain, it's not a good thing, it's detrimental. It could go to saturation, that means distortion. That means distortion. When voltage does not meet when the output voltage does not follow the input voltage, that's distortion. You don't want that. So, because it has high gain, and because we don't want to use such high gain, we use this device with feedback. With feedback, we can bring the gain to our control. We can bring the gain to what we can manipulate. We can take it up or down. That is the most beautiful part of op-amp. That's why we're so proud of op-amp. Is there anybody in doubt on what I just said in the last few sentences? The magnificence, the majestic part of this device is because I can use it with feedback and I can control the gain. That is the beauty of op-amp. Because the high gain of op-amp is not something to be proud of. In fact, if we offered it to a wise man or wise woman, they would say, well, no, it's not a good thing. Right. So feedback we must use. Okay. Now feedback can be positive feedback, or negative feedback. What do I mean by that? Okay, let me just show it in a crude form. I can take this output, feed it back there. I call this negative feedback. I can take this and feed it back there. I can call it positive feedback. Of course, I can do either. I can do negative feedback. I can do positive feedback. I am just asking you to bear with me, to just tolerate it for this semester, that we won't do anything with positive feedback at all now. In this semester, we will only consider negative feedback, please. That's what I'm asking. But then I also add by saying, when we feedback negatively, we improve the parameter of this whole circuit, which helps us in amplifying circuits. So negative feedback will help us to design better amplifiers. When we use positive feedback, it will not help us to make to decide or to design better amplifiers. In fact, it ruins it. But it will help us to design better filters, better oscillators, and better other circuits. And since in this semester, we only consider amplifiers, we only use negative feedback. Next semester, we talk about positive feedback. Right. Again, we want to use negative feedback. So in order for you to fully understand, I'm going to flip this device over and take this like here. It's just for you to understand better, that's all. Remember that guy at MIT also drew it like this? This is output. So what I'm doing, I am just going to apply a signal here, call it Vin, to the non-inverting terminal, and I am taking the output and feedback through this terminal. And if I do this, I want to see what is happening. Right. What is being seen by the op-amp here at between, or the difference between the terminals? Would you say it's Vin minus what the voltage is there? We call it what do we want to call it? I call it V feedback. How about that? Let's call it VF. Let's call it VF. So the Vin minus VF times A being the gain, is equal V out. That I can very safely say. The difference between the two terminals times the gain is the output. Let's now substitute. What is VF? VF is V out times R1 divided by R1 plus R2. Therefore, I substitute this for VF. I write down Vin minus V out times R1. R1 plus R2 all times A is equal V out. Since I have a V out here and a V out there, I just rearrange and say Vin times A is equal A V out R1 plus R2 plus V out. Oops. So all I did, I just rearranged this and I arrive at this. Okay, Vin or AVin is equal V out A V out A R1 plus R2 plus 1. Now I can say V out over V in. That is the actual gain with feedback. that is V out over V in, is now my new gain. Initially, the gain initially means without feedback. Initially, that is without feedback. Without feedback, gain was equal A. Now, gain, which is V out over V in, is equal to what? This is what I'm about to find out. With feedback. V out over V in is equal A over A R1. R1 plus R2 plus 1. Now look at the denominator. Would you not say that A times R1 over R1 plus R2 is much, much, much bigger than 1? A R1 divided by R1 plus R2 is much bigger than 1. Therefore, we can ignore 1 easily. Ignore 1. And therefore, V out over V in would be A over A R1 plus R2. A and A will cancel. I will have R1 plus R2 over R1, which would be V out over V in is equal 1 plus R2 over R1. That is the gain with feedback. So the circuit that I just flipped over, I'm going to flip it over again. These two circuits, that circuit is that circuit. I'd like you to have a good look at it. It's just that the op-amp is flipped by 180 degrees. Is it 180 or is it? Yeah, 180. And the gain is V out over V in is equal 1 plus R2 over R1. As you can see now, the gain is nothing but the ratio of resistors only. So let me draw the other possible. Last time, this is the circuit. This is R2. This is R1. I applied the signal to this terminal last time. I just put a V in there. This time I'm going grounded. and I'm going to apply the V in here. What is going on? I am going to apply, oops. I'm going to apply V in to this terminal this time. Okay, if this is V in, what would be the current? What would be the current I? I is V in over R1. This I is the same I that flows there. So if that current is through here, what is V out? V out is, of course, minus IR2, minus IR2. And V out is equal minus V in R1 times R2. Therefore, V out over V in is minus R2 over R1. So now, in summary, I'm going to draw two identical circuits. Here I can say V out is V in times 1 plus R2 over R1. Here I can say V out is minus V in times R2 over R1. I want you to look at these two circuits and tell me that you have no problem with either of them. So let's ask Isaac. Isaac, are you happy with this?
Okay, so for this last one, Kasai, with the VN going into the inverting terminal, you had the gain as
Oh,
V out.
thank you
the
very
gain.
much. This is like, I'm sorry. These
Okay.
two, sorry. You're right, thank you. So let me, it's here, V out is minus V in R2 over R1. Here is, I'm sorry about that. V out is equal to V in 1 plus R2 over R1. So you were going to correct me then? like this.
Looks amazing. Yeah, it's perfect. I appreciate that.
Very good. Thank you. Is everyone else okay?
Absolutely.
Super. Now these are really the two most fundamental, essential circuits for op-amps and op-amp circuits. Because whether we want to use op-amp in any form of other mathematical operations, you see, op-amps are obviously used for various things. But the application of op-amp is for solving problems, basically. Problems are usually expressed in form of mathematical equations, mathematical in the language of mathematics. Problems can be expressed in language of mathematics. And op-amps are the solvers. Op-amps are those devices that we can solve those issues, those problems. Now, in order to solve any problem, listen, this is scientific sentence, any problem, solve any equations, differential, integral, summing or subtracting or multiplying or dividing, I mean, any problem, any mathematical problem need to be solved electronically. There are two circuits, only two circuits that are fundamental to all solutions. Those two circuits are the ones. Remember when we're doing logic, we said and, or, and not are just the fundamental gates to all logic circuits. In analog, we can say those two circuits are the fundamental circuits to all analog problems. So there should be nobody who can go to next level of education, to next semester, without knowing these two. All right, so these two circuits, and yet they are so simple. There's absolutely no problem, because the feedback are identical to both cases. Whether we apply the input signal to this terminal, to the inverting terminal, the gain will be that much. And if we apply the input signal to the non-inverting terminal, the gain will be that much. So what's the problem? I mean, that's as simple as that. And both you can, even if you forget, you can just prove, you can easily prove what I just did. Okay. Now we can go to application. Oh, before we go to application, there are just two more things that we must really kind of bear in mind. And that is the difference between, okay, let me just draw another one. This is inverting terminal, this is non-inverting terminal. These are the supply and that's the output. The difference between this terminal and that terminal is really not much. The difference is not much. In fact, the difference is nothing. The maximum difference, maximum difference between these can possibly be is just 15 microfarad. Microvolt, I mean. The maximum difference between these two terminals can only be 15 microvolt. because if these are 15, I mean, don't forget when I say, for example, 15 volt minus 15 volt, that's what op-amps supplies are. I mean, if you look at the data sheet, they say that the supply voltage is about 15 volt. And since the 15 volt you apply, this is V in, this is V in, that's V out. So it's something like this. Anything above the 15 volt, that thing you will go to saturation, of course. So we can only go between plus 15 volt to minus 15 volt, no more. Microvolt, I'm sorry, microvolt. The difference between these two can be maximum of 15 micro. For example, here would be minus 15 microvolt. If we applied it here, would be plus 15 microvolt. The difference between these two can only be maximum of 15 microvolt, no more. And in engineering terms, 15 microvolt means zero, means nothing. This is same as saying that if this terminal is grounded, this is virtually grounded. That is something that we must remember. If this terminal is grounded, that is virtually grounded. That's one other thing we must remember. As well as those two circuits, we must remember this. So based on these information, let's see if we connect an op-amp this way. Say, I just connect these 3 resistors there and there. Based on what I just learned, call this R, I call this R, 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 and then I call this V1, call this V2, and I call this V3. I call this V out. V out would be minus V1 plus V2 plus V3. That means the summing amplifier. Why? Why is that the case? Because when we consider this input, V1, we can consider this to be grounded and that to be grounded. And if these are grounded, there's no voltage is connected, that means there's nothing. If there's there's nothing. That means V out 1 would be minus V1 times R over R. And the R and R cancel is just minus V1. V out 2 is minus V2 times R divided by R is minus V2. And V out 3 is just minus V3 times R over R, which is minus V3. Therefore, V out is minus V1 plus V2 plus V3. Summing amplifier with obviously a negative sign, which we can get rid if we need to. Let me just do this subtracting as well. And we call it. Are we just going too fast, I guess, huh? Are we good? Are there any questions? Have I put anybody to sleep?
No, I think we're good.
Sorry, who was saying what?
We're good.
Good, 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 good. So let me just do one more circuit and then we stop today. I mean, that's good enough. Because unless you want to, it's best not to. Let me just do one more, the subtracting circuit. That would take us, I mean, that's like 1 hour, 45 minutes. It would be enough for today. And then tomorrow, we listen to presentations in the morning, and then we can spend 2 more hours in the afternoon. That would be better. Incidentally, before I forget, when I finish tomorrow afternoon, that I'm hoping that all the review will be ended by then, you, at any time, please, if you are doing your own review and you want to email me or come back to me and just call me, whatever, and say, I have this question, please feel free to do so. You have till next Monday, right? The exam is next Monday, am I right? Yeah. So from tomorrow afternoon, you can come back anytime you want. Oh, and that reminds me again, did you all please go and kind of address the survey? Please, I wrote to you last night asking that if any one of you would just do the survey, please. And this survey, I have two reasons for asking you to do that. One for personal reason and one for my position. I just like you to make your point of view heard so that I know who to invite and not to invite for semesters and what. So please be as honest and responsible and as frank as you can possibly be with these feedbacks. Because it's anonymous. Nobody would know who has said what. It's just the points of view will be heard and listened to. And I will read everybody's, all other instructors, I will read them all. But each instructor read their own. All right. Now, if I have this. If I just have V1 and V2, R1, R2, call it R1, R2. Now, the reason I call them R1, R2 for now, because if I put them all R, then I won't be able to, it would be confusing. It's best to call them R1 and R2. Then we can say R1 is equal R2 is equal R. That's if we want to, which will make it a lot simpler. But at the moment, we call them R1 and R2. Now, what would be the V out equal to? V out. Well, here, remember the two circuits we had earlier? The two circuits told us that the feedback is R2 over R1. Feedback is this over that. That feedback is still the same. But then we applied the voltage either to this terminal or to that terminal. But here, in this case, in this circuit, we are applying the V to both terminals. If we are applying voltage to both terminals, we must apply superposition. superposition theorem tells us. This is what is superposition? The superposition theory tell me, when you want to consider voltage to this terminal, you assume this terminal is grounded. Then, and you take the output based on this voltage. You take the output based on just this voltage, because this voltage is grounded. Then afterwards, you assume that this terminal is grounded, and you just apply voltage to this terminal and find out the output, and then you add the both results together. That is applying superposition. Here, I call it V out 1 is equal minus V1 R2 over R1. Of course, this is what we did. This is grounded, and if grounded means there's nothing, and therefore output voltage is based on this V1 is just minus V1 R2 over R1. Now, this is case 1. This is case 1. Case 2, I'm going to ground this and just take V2 here. V2 is being applied. What is V out 2 equal? V out 2 is, because the voltage is applied to the non-inverting terminal, is of course 1 plus R2 over R1. This R2 over this R1. The feedback, the voltage which is applied here, is that the 1 plus R2 over R1 of here. And these, of course, are the feedback. This is the feedback part. This times whatever voltage is applied there. Whatever voltage is applied there. For now, I'm calling it V2 prime, because I don't know what that is. Surely the voltage which is applied here is not the same as that voltage. This is V2 prime. This voltage is V2 prime, is not the same as this V2. So I can't just put V2 there. I have to put V2 prime. But then V2 prime is equal V2 times R2 divided by R1 plus R2. And I can substitute for V2 prime. Therefore, V out 2 is 1 plus R2 over R1 times V2 R2 R1 plus R2. Now here, I can say V out 2 is equal V2 R1 plus R2 times R2 R1 plus R2. This R1 plus R2, this R1 plus R2 cancels. So V out 2 is V2 R2 over R1. We must add these two together. V out is V out 1 plus V out 2, and V out is minus V1 R2 over R1 plus V2 R2 over R1. And I'm going to take V out equal R2 over R1 V2 minus V1. And if R2 is equal R1 is equal R, then V out is V2 minus V1. That is, the output voltage is the